Welcome back. I imagine by now you're starting to realize what a great cheat sheet your periodic table is. Let's look at some additional patterns or trends in chemical behavior that can be predicted by the periodic table. We say trends because certain chemical properties follow a general pattern when you look across a period or down a family in the periodic table. But even though each individual element might not follow every trend, the trends will help us understand chemical reactions.
In this lesson, you will explain the trends in atomic number, atomic mass, atomic radius, ionization energy, and electron affinity as you look across a period and down a family of the periodic table. Define atomic radius, ionization energy, and electron affinity. Define ion and predict the charge an atom of an element will have when it forms an ion, based on the element's location on the periodic table.
Today, you are going to be part of a living periodic table in order to investigate some properties of the elements and the patterns the properties follow. Your local teacher has set up the desks into 4 rows, or periods, and 7 columns, or families. Each desk represents an element. You are the element for the desk you are sitting in. The first thing you will do is fill in some information about yourself. Let's peek in on a student who's doing just that.
The student is sitting in the phosphorus desk, so she is phosphorus. She finds phosphorus on the periodic table and the chart provided by her teacher. She also looks at her filled-in periodic table from the last program. She uses these 3 items to fill in information about herself. The student notes the exceptions listed on the phosphorus description on her desk. The student marks these exceptions on her data sheet.
Your local teacher is going to pause the tape now for you to fill in the information about yourself. Be sure to note the exceptions about your element. Our object today is to look for some general trends that occur on the periodic table. There are cases where every element does not follow the general trend. This is why you must mark down the exceptions. Local teachers, please pause the tape while each student fills in information about the element he or she represents. The next step in the living periodic table is to find out how the elements around you compare to you in terms of relative mass, electron distribution, ionization energy, atomic number, atomic radius, and electron affinity. Whew. Are you ready, Cecil? Then let's peek in on our student again to show us what to do.
The student is going to ask her neighbor, who is playing the part of arsenic, some questions and fill in the answers on her chart. Arsenic has more mass than phosphorus, so the student writes more in her chart. The electron distribution end for arsenic is 4p3. Arsenic's ionization energy is less, so the student writes lower in her chart. The student writes higher for atomic number and larger for atomic radius. The student doesn't need to find out about electron affinity because she was told this is an exception. Now the student turns to another neighbor to find out information about nitrogen. Nitrogen has less mass, a distribution of 2p3, a higher ionization energy, a lower atomic number, a smaller atomic radius, and she doesn't need to ask about electron affinity. Now the student turns to another neighbor to find out information about silicon. Silicon has less mass, a distribution of 3p2, a lower ionization energy, a lower atomic number, a larger atomic radius, and she doesn't need to ask about electron affinity. Now the student turns to another neighbor to find out information about sulfur. Sulfur has more mass, a distribution of 3p4. She doesn't need to ask about ionization energy, a higher atomic number, a smaller atomic radius, and a higher electron affinity.
Now that you have an idea of what it is you are supposed to do, your local teacher will pause the tape for you to find out about the elements around you. While you are conversing with your neighbors, you might want to find out who sulfur has a date with this weekend, but don't forget to focus on the element information. Have fun. My students and I will be back to show you the next step. Local teachers, please pause the tape for your students to interview their element neighbors. You having fun? I hope so, because you're not finished yet. You're going to find a new seat so that you can be a different element, just as you see my students changing seats. Once you've picked a new seat, you will write down all of the information about the element you represent, and then find out about your neighbors, just like before. You got that, Oxygen? You will continue until you have sat in the seat of 4 different elements. Local teachers, please pause the tape for your students to continue participation in the living periodic table. It's time to improve your cheat sheet by expanding on your knowledge of the periodic table. You're going to look at the information you gathered about many elements to answer the following questions, which your local teacher will put up for you. You want to answer the questions for each of the properties you investigated in your living periodic table: relative mass, electron distribution, ionization energy, atomic number, atomic radius, and electron affinity. Then, we will discuss what you found out about each of these properties. Here are your questions. What trend does the property follow as you move across a period of the periodic table? And what trend does the property follow as you move down a family of the periodic table? Local teachers, please pause the tape and put up questions for your students to answer.
Okay, let's see what you found out. We're going to start with atomic number because that's the most straightforward. I want you to tell me what happened as you go across the period and down the family to the atomic number.
Well, it increases as you move across the period and down the family. And this makes sense because this is the basis of organization for the periodic table.
Exactly. I couldn't have said it better myself.
As you move across a period and down a family of the periodic table, the atomic number increases because the elements are arranged by increasing atomic number.
Now let's look at atomic mass. Let's see what atomic mass does as you move across the period and down a family.
Well, it gradually increases as you move across the period, except for in a couple of places. It also increases as you move down a family, in some cases by a whole lot.
That's
right, and don't worry about the exceptions,
because we're just looking at the general trend.
As you move across a period and down a family of the periodic table, the atomic mass generally increases.
Before we look at our next trend, I want to make sure that you know what we mean by atomic radius. It would be easy to define if the atom were a perfect circle, but it isn't. We could say that the radius of an atom is the distance from the center, or nucleus of the atom, to its edge, except that it's hard to find its edge. For this reason, atomic radius is determined by looking at two atoms of the same element, side by side. The nucleus of each atom is clearly defined, so a measurement can be made from nucleus to nucleus and divided in half to determine the radius.
Atomic radius is defined as 1/2 of the distance between the nuclei of two like atoms.
Okay, now let's look at the trend in atomic radius. Let's look at atomic radius and see what it does as you go across a period and down a family.
Well, as you move across the period, it decreases, but as you move down a family, it increases.
Does that make sense to you?
Yes, because as you add energy levels, the atoms obviously get bigger for the family. But I'm not sure about the periods.
Okay, well think of it this way. It's the attraction between the nucleus, the protons in the nucleus, and the negative electrons that hold those electron clouds in place, right? Okay, well think about it. As you go across the period, what happens to the
number and energy levels?
It's the same, right? And what happens to the number of protons in the nucleus? It gets larger.
Okay, I get it. So as the number of protons increases, it forms a stronger attraction between the electrons and the energy levels.
Right, and that stronger attraction pulls the electron cloud in just a little bit, making the atoms get smaller as you go across.
Atomic radius decreases as you move across a period due to the increased attraction between the positively charged nucleus and the electron clouds. Atomic radius increases as you move down a family due to the addition of an energy level with the addition of a period.
You also looked at electron affinity. Let's talk about this property before we discuss its trend in the periodic table. First of all, affinity is just a natural attraction for something. So electron affinity would be a natural attraction for an electron.
Electron affinity is defined as the attraction an atom has for an electron, which is represented by the amount of energy an atom releases when it gains an electron. An atom with a strong affinity will release a large amount of energy.
Okay, now let's look at electron affinity. What happens to electron affinity as you move across the period?
Well, generally it increases.
Can you explain that?
The closer you get to the noble gases, the fewer electrons it takes to stabilize the atom, and so therefore there's a stronger attraction between the electrons and the nucleus.
Exactly. Now, what about as you move down a family, what happens to electron affinity?
Well, there are a few exceptions, but generally it decreases. And if you think of it in adding electrons to energy levels farthest from the positive nucleus.
Right.
Electron affinity increases as you move across a period and decreases as you move down a family.
Another property we looked at is ionization energy. Again, we can figure out its meaning from its name. Basically, ionization energy is the energy necessary to make an ion. But it's a little more than that. It is the energy necessary to make an ion by removing an electron.
Ionization energy is the energy required to remove an electron from a neutral atom.
All right, finally let's look at ionization energy. What happens to ionization energy as you go across a period, down a family?
Well, it generally gets larger as you move across a period, and smaller as you come down a family. That's the opposite of the radius trends, and that makes sense because as you get closer to the nucleus, it takes more energy to pull electrons away.
That's right.
ionization energy increases as you move across a period and decreases as you move down a family, because the smaller a neutral atom, the more energy it takes to remove an electron.
The other characteristic we looked at today is electron distribution. We talked last time about this trend, but let's look at it again in terms of forming ions.
Sodium atoms and all the alkaline earth metals that share group 1 of the periodic table with sodium achieve a stable octet by losing one electron and forming a positive ion, while chlorine and all the halogens that make up group 17 achieve an octet by gaining an electron and forming a negative ion. Often, other elements have to lose or gain more than one electron in order to achieve a stable outer energy level. For example, oxygen and sulfur in group 16 have to gain 2 electrons in order to achieve a stable electron configuration, which causes them to form ions with a net charge of -2, while calcium and magnesium in group 2 have to lose 2 electrons and form +2 ions in order to achieve stability.
An ion is simply a charged atom, and an atom becomes an ion by losing or gaining electrons. Both of the elements' electron affinity and ionization energy relate to the formation of ions from neutral atoms. Remember that an atom is stable when it has a full outer energy level, which means 8 valence electrons. Let's look at our 8 main families and see what types of ions they will form. You know that the alkali metals have an S1 electron distribution, which means they have 1 valence electron. There are 2 ways for atoms to achieve a full outer energy level. They can either gain enough electrons to have 8, or they can lose all of their valence electrons, leaving a full outer energy level on the next level down. Let's look at this possibility more closely. Sodium has an electron distribution of 1s2, 2s2, 2p6, 3s1. If sodium lost its 1 valence electron, now the second energy level would be the outer energy level. And there are 8 electrons on this second energy level. So this sodium ion would be stable. This is always the case. If an atom loses all of its valence electrons, the next level down has 8 and makes a stable ion. So, all of the elements in the alkali metal family will form ions by losing an electron. Or we might say that they give an electron away. Since electrons have a negative charge, an atom becomes a positively charged ion when it gives away an electron. Of course, this is easy to remember because it is positive to give. Since the alkali metals give away 1 electron, they have a positive 1 charge. Now let's look at the alkaline earth metals. They have 2 valence electrons. It makes more sense for them to give these 2 away than to try to gain 6 more. So they form positive 2 ions. How about the boron family? They have 3 valence electrons. They give them away, and they form positive 3 ions. Now, the carbon family is a little tricky. They have 4 valence electrons. So it makes as much sense for them to gain 4 electrons as to give away 4 electrons. We can think of gaining electrons as stealing electrons, which will help us remember that an ion is negatively charged if the atom has gained or stolen electrons, because it is negative to steal. So the elements in the carbon family can either lose 4 electrons to have a positive 4 charge, or gain 4 electrons to have a negative 4 charge. The nitrogen family has 5 valence electrons. These elements will gain 3 electrons to achieve stability. Gaining or stealing 3 electrons results in a -3 charge. The oxygen family has 6 valence electrons, so they will gain 2 electrons and form -2 ions. The halogens have 7 valence electrons, so they will form -1 ions. And the noble gases will neither gain nor lose electrons because they are already stable. Remember that helium is stable with 2 electrons in the first energy level, and all the other noble gases have a stable octet in their valence level. Get out your handy-dandy cheat sheet, otherwise known as the periodic table, so you can fill in the charges at the top of each column. And we'll wrap this lesson up. Local teachers, please pause the tape while your students find their periodic tables. At the top of the first column, write +1, then +2, +3, positive or -4, -3, -2, -1, and 0. When we get the formula ready, your cheat sheet is going to come in very handy if you have memorized these patterns and charges for ions. And now, it is time for your chemistry quiz. Of course, you will want your cheat sheet in hand while you work. Cumulative energy question 1. The lowest energy state of an atom is called the A. Excited state, B. Ground state, C. Independent state, D. Configurational state.
Cumulative review question number 2. What is it about the elements in a column of the periodic table that makes them behave similarly? A. Atomic number, B. Atomic mass, C. Electron distribution.
Number 1. Use your periodic table to determine which of the following elements has the largest atomic number. A. Na, sodium. B. K, potassium. C. Li, lithium. D. Rb, rubidium.
Number 2. Use your periodic table to determine which of the following elements has the largest atomic radius. A. Carbon, B. Nitrogen, C. Oxygen, D. Fluorine.
Number 3. Use your periodic table to determine which of the following elements has the largest ionization energy. A. Iodine. B. F. Fluorine. C. Cl. Chlorine. D. Br. Bromine.
Number 4. Use your periodic table to determine which of the following elements has the largest electron affinity. A. Phosphorus, B. Silicon, C. Chlorine, D. Sulfur.
Which of the following is the correct noble gas distribution for chlorine? A. 1s2, 2s2, 2p6, 3s2, 3p5. B. Neon, 1s2, 2s2, 2p6, 3s2, 3p5. C. Neon, 3s2, 3p5. Hey, Nitrogen, how did you do? Your local teacher will go over the answers with you in a minute. You will be finishing up this unit and testing soon, With your cheat sheet in hand, you'll be just fine. Remember, however, that the cheat sheet will only be useful to you if you understand how to use it. So study it. Understand it. Know it. Keep it close to your heart. See you soon.